Welcome to class meeting 10 of the Introduction to Optimization Theory. First, I have 3 announcements. As you see here, we have agreed on the first midterm date, which is March 31st. And this is time, place, and coverage. Okay? So it's up to the Newton's method to be taught this Wednesday. Homework 2 is due on this Wednesday, and I have given you 3 additional problems. Those solutions, whose solutions are found in the textbook. Okay, so you prove some main results of chapter 8. I need to make a correction. It's not a major one, but when I draw a Venn diagram to give you a big picture of chapter 8, it could be said an error, or it could be not an error. But anyway, I will make a correction. Okay. Before we review what we learned last time, this is a kind of big picture, a little bit zoomed out version of where we are. Okay. In chapters 1 through 5, we covered preliminary results from your undergraduate study, like methods of proof, and some linear algebra materials, and some multivariate calculus materials. And then in chapter 6, we considered general set-constrained and unconstrained optimization problems. Especially, we studied necessary conditions and a sufficient condition. So we studied first order necessary condition, first order second order necessary condition, and second order sufficient condition. And then we studied some one-dimensional search algorithms like bisection method, golden section method, and Fibonacci search algorithm. And then last time we started to study chapter 8 about gradient methods. By the way, the next chapter is on Newton's method, and you may say that, wait a minute, in addition to those bisection, golden section, Fibonacci, we studied Newton's method of tangents and Newton's method of secants. Of course, at that time we studied a Newton's method for one-dimensional search. Now here we study Newton's method for n-dimensional search. So actually, what you learned here is related to chapter 9. And chapter 9 will be covered very fast. So kind of these chapters completes the coverage of the first midterm. Got it? Okay. Next, let's summarize what we learned last time. So we started to take a look at this general iterative algorithm form, general form of an iterative algorithm in our search for local minimizer. So from the kth iterate, in estimation theory, you may say that this is an estimate, the kth estimate. But this estimate somehow means that our optimization problem is related to estimation problem. Since it is not always true, the textbook says this is kth iterate. Okay? So when you iterate, this is the kth entry. So kth iterate. Okay? Then this is the k plus 1th or k plus 1st iterate. So from the kth iterate to the k plus 1th iterate, we can view this update as adding a vector also in Rn as xk and xk plus 1. We only consider optimization problems where our objective function is from what? From Rn to R. So this kth iterate and k plus 1 iterate both lie on the n-dimensional Euclidean space with well-defined and well-known Euclidean norm, the squared distance, square distance metric. Okay. So there exists a vector, and we may factor this vector into the kth step size alpha sub k and the kth search direction d sub k. Okay. For convenience, when we say alpha sub k is a step size, we restrict it to a non-negative number so that this d really is the direction of search. Okay. From xk, you move toward this direction. Of course, there could be many other vectors, like, for example, if this is 2 and this is some vector d, you may say that step size is 1 and the direction is 2d. Okay? We even have that ambiguity. We somehow say that our difference of these two iterate is a product of the step size and the search direction. Now, given that the first subclass, first class of our iterative algorithms is a gradient methods. So it's like here you have the set of all iterative algorithms. Then there's a very small set, say G, which contains all gradient algorithms or gradient methods, where our kth search direction is what? The negative gradient of the objective function at the kth iterate. Okay. For convenience, we set this first order derivative of f as g. So here you may say that the direction is minus g sub k. Right? So this is our notation. Even though this set is very small, I will little bit exaggerate so that we could see clearly around here. And that was this. Okay. So from the step size, let me move a little bit of this. Okay. So this is the set of all iterative algorithms. Okay. So first we focus on this step size. There are basically two algorithms according to how to choose our step size. First, fixed step size algorithms, and second, variable step size algorithms. So here, this is the subset of all variable step size algorithms. And then we have this set of all gradient algorithms. And another property that is not necessary, but it would be good to have is the what? Descent property. What does that mean? When you iterate, your objective function decreases. Okay. So here is the set of all descent algorithms. Now, given that this corresponds to this small subset corresponds to this one here. Okay. Now, last time I said that we are going to study one algorithm reside here at the intersection of all these three: variable, gradient, and descent properties, satisfying these three properties, and one that is fixed step size, which is outside this one, and gradient, but possibly not having this descent property. But actually, of course we consider all these, but mostly we not talk about this one, but talk about that one. Okay. So last time I said that we are interested in these two. Actually, these two. Got it? Okay. So again, gradient algorithm. Algorithms are our interest in this chapter. Okay. So how many? 1, 2, 3, 4. 4 classes. Among these 4 subsets, we have one algorithm here and one algorithm here to study. Got it? Yeah, that is the correction. Okay. Given that, we need more to review. So first, an important property of the so-called the steepest descent gradient method or algorithm. What was that? By the way, steepest descent is one of the gradient algorithms. So gradient, that qualifier is missing, but it is given like this. Okay. So the k plus 1th iterate is defined as the argument. So I put arg here. Argument that minimizes, because our standard form is to achieve the minima, minimize the function value at the kth iterate plus some alpha times the negative gradient. Okay. Let me see. Yeah. Here, the argument, the variable alpha is greater than or equal to 0. Okay. So be careful. Some people love to put this kind of search space below arg mean, but some people say that, wait a minute, this is an optimization problem, and we have our argument returned. So some people love to put this alpha greater than or equal to 0 only below this mean. It depends on the preference of the writer. Okay. Anyway, here this means that in this minimization problem, alpha is our objective parameter, objective function. So you find alpha and set it. Sorry, this must be alphas of k. Okay, so this becomes the kth step size. Okay. When you have this one, so let me state a little bit clearly. So first definition, the steepest descent algorithm has two components. One, the k plus 1th iterate equals the kth iterate plus alpha sub k times the negative gradient. Okay, as all gradient algorithm satisfies. And second, alpha is chosen this way. Okay, so these two lines kind of characterizes the steepest descent algorithm. Now, kind of lemma is that here, unless, okay, in the second step, unless grad f of xk is 0, there exists alpha bar such that alpha between 0 and alpha bar implies f of xk plus alpha minus gradient is less than f of xk. Okay. So this means that if you move to the opposite direction of the gradient, okay, there always exists a very small step size that reduces your objective function value. Okay. By the way, this property is for general gradient methods. Okay. But depending on how to choose your step size, your specific gradient algorithm may fully utilize this property or not. Okay. But what is good is that as you see here in the second step, okay, steepest descent exploits this property. So what? It has descent property, as the name says. Okay. And another thing, another interesting property, now this is for general gradient algorithm, and this is for steepest descent gradient, is that your kth such direction and k plus 1 such direction is always orthogonal. Actually, these two properties, both satisfied by the steepest descent gradient algorithm, states the strengths and the weakness of this steepest descent algorithm. How did you state? Okay, by using this one, we could say what? Okay, steepest descent algorithm has descent property. That is good. But here, what does this mean? If this is the k such direction, use k plus 1's direction is orthogonal. And you may say that that's okay, but restrict your interest to, for example, a quadratic objective function with very different eigenvalues in 2 dimensions, for example. In that case, instead of going directly to the local minimizer, you may have very large iterations because you always move like zigzag type. So this may be understood as a weakness of the steepest descent gradient. And then we had a very interesting results that only holds for quadratic objectives. The reason why we restrict our interest to quadratics is that it is easy to analyze the performance of our algorithms. Okay. So generally, a quadratic objective function from Rn to Rn is given like this. If you remember your high school or middle school math, Okay, that 1/2 is just for scaling purpose. Okay, but this is not good for clever analysis. So instead of using this one, what did we use? We considered some function called v, and that has in this form. And you may say this is too not general, special, but actually it is general enough. Let's expand this one. Then the second order term is same as actually half x transpose qx, as you see, right? And what? You have a first order term that is what? Q minus qx star. Okay? And you have the constant term that is 1/2 x star transpose qx star. Okay? So given any quadratic function, actually by adding a constant term, you can put it in this complete square form. Okay? And it's kind of does not lose any generality when we analyze the performance. The good property of using this v function instead of this general quadratic function is this. First, this v of x is always non-negative, right? Because it's a complete square. By the way, here we are going to assume Q is a positive definite symmetric matrix. Okay. Which means that it allows orthonormal eigenvalue decomposition where eigenvalues are all real positive values. Got it? Okay. So given that the first property is this objective function has non-negative value and with equality holds, which means that equality if and only if x is x star. Okay? So it has the unique global minimizer. Okay? And at this global minimizer, this function value is 0. Okay? Otherwise, the value is positive. Okay? This is a very good property for us to use, as you will see today. And what is the second one? Second property is also quite interesting. Now this is for gradient method. Okay. Okay. So be careful. Okay. This is for general. Okay. This is the general property of this function. And now here we have something interesting. We can just let me remember where it is. Just a second. Where it is? Okay. So here, v x sub k plus 1 equals 1 minus some gamma k times v of x sub k, okay? Where gamma sub k equals alpha sub k gk transpose q gk divided by gk transpose q inverse gk times 2 times little bit different quantity transpose q gk minus alpha k. Okay. So suppose we apply any gradient method, okay, to this objective function. Okay. So we don't know what is our alpha sub k because we said what? General gradient algorithm. But we have what? Our search direction is minus g sub k. Okay. So here this minus g sub k is our k search direction. Okay. And by the way, what is this? Can it? Yeah. If we apply this to this direction to this quadratic optimization problem, then what else? Yeah, I think this is just, yeah. So anyway, you can derive this one. Okay. Now here, okay, this is non-negative, right? As you've seen here. And this is also non-negative. What does that mean? This factor 1 minus gamma sub k also must be non-negative for any algorithm. Okay? Right? For any algorithm. By the way, actually, this rewriting can be done for any algorithm, including gradient algorithms. But anyway, here we say that this holds okay for any algorithm, and especially gamma sub k is given in this form when we consider gradient methods. Got it? Okay. So interestingly, as you can see, this value, what if this value is less than 1? The function value at kth iterate is greater than, if this is less than 1, then the k plus 1 function value. So we have descent property, right? So if this is the first one, second one is that if this is then descent. Okay. What does that mean? Here, gamma sub k can be a negative number for some k and for some algorithm. Then what happens? This is a negative 1, which means that this 1 minus gamma sub k may be greater than 1. What does that mean? You do not have descent property satisfied at the kth iteration. Okay. But it's okay. It's okay. Okay? Descent property is a good property, but it's not a necessary property. Gradient methods, choosing the direction as a gradient of the function is also a good strategy in some sense, but it's not necessary. So this is very important. Okay? For what? For gradient algorithms and what? For quadratic objective function. Okay? And proving this one was one of your additional homework problem. Got it? Okay. Now, given that, what did we do? We applied this result for steepest descent. So, it's like all iterative algorithms are here, and variable, step size, gradient, and descent, and here is the steepest descent algorithm, right? And now we apply this one to quadratic, especially the v of x. Now, what is alpha sub k? Since our steepest descent algorithm specifies how to find alpha sub k. You can find alpha sub k and substitute it to here, right? By replacing this alpha sub k's. So first thing you need to do is to find that alpha sub k, and that was another steepest descent applied to v of x. What was that? Alpha sub k was given by g sub k transpose g sub k divided by g sub k transpose q times g sub k. Okay? So if you replace it to the algorithm, actually what do you have? You have the k plus 1th iterate equals the kth iterate minus g sub k transpose g sub k transpose q g sub k g sub k. Okay? There are many g sub k's, but they are all negative gradient of the objective function evaluated at the kth iterate. Be careful. You may say that, okay, well, why me repeatedly saying that this is applied to quadrats, blah, 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 because it's confusing when you study. But one tip is this. Whenever you see this q, of course it is for v of x, right? Because this q means that we only consider a quadratic function. Okay? So say that you consider the steepest descent algorithm, and if you plug this in, then you have this result. Only for what? That v of x having this positive definite symmetric matrix Q. Got it? Now, of course, you can substitute this one to what? To the previous one and see what happens. Okay. So, continued. And now let's have some computation. Okay. But before doing that, okay, it seems that I missed one important property here. Okay. Let me see. Just a second. Yeah, third one. Here goes the third property. Okay. It is related to this second one. Okay. So now let's focus on this line only. Okay. It is not, the algorithm is not necessarily a gradient algorithm. Okay, so only for this one. Okay. So just for general quadratic objective functions. Okay. One thing interesting happens. Okay. Your algorithm generates the kth iterate that converges to the global minimizer if and only what? If and only if that step size, not step size, that gamma sub k, when they are summed, blows up. But actually, here we need to have some constraint. This is only true when every gamma sub k is positive. Okay. So this is not for general. For example, what does this mean? What does this mean? Okay. It is related to this descent property. Okay. So as far as your algorithm, any algorithm, including steepest descent or some gradient, satisfies the descent property, then your convergence is guaranteed if and only if this gamma sub k is a sum blows up. Okay. And one of your additional homework problem was to prove that this is true, okay, for this quadratic function. Okay. And probably you've done this or you are going to do it to submit the second homework, and it is related to which one? This one. So if you plug in here the 1 minus gamma sub k minus 1 v of x k minus 1 and repeatedly substitute, you will see product of 1 minus gamma sub k's. If this infinite product converges to 0, if and only if this holds. Okay? So you will actually shows that the sum of gamma sub k's blow up if and only if product of 1 minus gamma sub k's tends to 0. And that is your homework problem. Anyway, so given that three results, if we focus on this gamma sub k, okay, so here we plug this alpha sub k of the steepest descent. Okay, question.
방금 블로우업이라고 하셨는데 아까 거기는 그냥 0보다 크다 돼 있는.
Sorry, infinity. Okay, equals infinity, I believe. Sorry. Okay, sorry about that. Yeah, goes to infinity. Okay, good point.
그리고 하나 더 질문.
Okay, one more question.
저기서 디렉션이 그 보통 노멀라이즈에서 그냥 크기가 1로 해서만 쓰나요?
No, not necessarily. So that's why I said that your step size and direction is not uniquely determined, even though your difference between the k and k plus 1's iterate is given. This is for convenience. Okay? But in the gradient method, you just view d sub k is always minus a negative gradient. Then every other thing becomes your step size. It's just for convenience. Anyway, so let's compute this gamma sub k. So this holds for what? Holds for steepest descent and for that quadratic function. Okay. Then what do we have? We have, let me see. We have this one. Okay. So from here, our new results we study. So up to this page 4, they were all reviews, and from here we study something new. So if you substitute, you can easily see that this gamma sub k for steepest descent and for this quadratic objective, you have g sub k transpose g sub k. This is scalar, right? Because it's an inner product of the same vector and squared. Divide by g sub k transpose q g sub k times g sub k transpose q inverse g sub k. Okay. I will not ask you to add this one to your homework. This is too simple, just substitution. So this is not a new additional problem. But anyway, you can have this one. Okay. So let's remember. Okay. So we have steepest descent. We know, given a quadratic objective function, we know what is our direction. Okay? We know what is our step size. And now we know what is our gamma sub k that relates the k plus 1th iterate and the kth iterate through this formula. Am I right? Now, what is a result that is too good to be true? These gamma sub k's are all positive, and when they are summed, their sum goes to infinity. Then what can we claim? We can claim the steepest descent algorithm applied to a quadratic function with positive definite symmetric Q function. This steepest descent algorithm always converges to our global minimum, right? So first, let's check whether this is positive or not. Okay. First, unless this g sub k is 0. What does that mean? If g sub k is 0, if and only if we already achieved our global minimum. So let's remove that case. Okay? Let's assume G sub k is a non-zero vector. The numerator is positive, right? Now let's see this one. What is this? This is a quadratic form. And what? This is not zero. And we assumed that eigenvalues are all non-zero. Then this is positive. Now what about this one? So you need to remind this one. Suppose you have the orthonormal eigenvalue decomposition like this. Here V is an orthogonal matrix, orthogonal matrix, and lambda is a diagonal matrix that has all eigenvalues. Let's say they are ordered in the decreasing order. Okay? Suppose. Then what can you say about this Q inverse? Is it a positive definite matrix? And what are the eigenvalues? And you can easily show that Q inverse is simply V lambda inverse V transpose. What does that mean? Inverse of these eigenvalues replaces this one. So again, Q inverse is positive definite. Okay. What does that mean? This quadratic form is also positive. So they are all positive. 1, gamma square is all positive unless G sub k is 0. Okay? That's some k. So this gamma sub k satisfies our previous result. That is related to the global convergence of our algorithm. Okay, what would be the second one? What would be the second one? This is related to what? The descent property. Even though it descends, an algorithm may not converge to global optima. Consider this one. Okay, suppose here is your Achilles, and here is your turtle. Okay, and what happens? For example, if this length is 1 and Achilles moves at every step 1/3 raised to the power of n, what happens? As you learned, he cannot reach this turtle. Okay? Even though it approaches, okay, monotonically. So be careful, right? Descent property does not guarantee, descent property itself does not guarantee global convergence. Okay? So second one, of course, this Achilles and turtles story by Zenon was totally wrong. Actually, Achilles keeps up with the turtle and even overruns, right? Anyway, forget it. I just gave you some stupid example. Anyway, now if we have this property, okay, then it would be good, right? Or actually, the equality is okay, because if this is 1, what happens? We achieve the global minimum, right? So we hope to show this. How can we show this? And if you take a look at our lecture note, see that? There it is. Yeah. Here, the authors remind you the Rayleigh inequality. This appeared already once, right? And this is very important in the sense that given a positive definite symmetric matrix Q, any quadratic form is bounded by what? The norm square of this vector x times the maximum eigenvalue and norm square of the vector times the minimum eigenvalue. So the quadratic form has upper and lower bounds in terms of the maximum and minimum eigenvalues. Got it? So this Rayleigh's inequality is very important, and we are going to use this to show that gamma sub k is what? Is greater than, is it greater? Yeah, greater than 0. Am I right? Sorry, less than 1, right? Yeah, less than 1, less than or equal to 1 for all k. And it says that, anyway, in the end, we have global convergence. And when I was at your stage, I got confused. So I'm going to explain this step by step. Okay. So here, okay, let's take a look at this gamma sub k first. Can you easily see that this is less than or equal to 1? Okay. Let's take a look at this numerator. How many g's do we have? 4 of them, right? So actually, if we distribute each of them, how can we simplify this? We may replace the numerator to 1 and denominator is what? Normalized version of gk's. Right? So in that sense, we little bit simplify this. Now, what about this one? Okay. So here goes a trick. Okay. Suppose you want to show something, some exact value. It may be difficult. In that case, try to prove an inequality. And that is a trick. So let's do it. So gamma sub k is what? Can be written in this way. Transpose q of same thing. Right? It's too complicated, but it's worth to do. And similar thing with inverse, right? Am I right? Yeah. So this is our gamma sub k. And now let's try to, for example, find the minimum and maximum of this. Or let's try to find the upper and lower bounds of this value. Okay. We found the lower bound already. 0, right? But we may improve that one. Okay, so let's try to find the maximum value of gamma sub k. And you may say that, wait a minute, does this make sense? For example, we have chosen our zeros iterate or initial guess of our solution and apply the steepest descent algorithm. Then deterministically every g, consequently every q gamma sub k is determined. How can we maximize? We can maximize this one at case value by randomly by choosing the zeros iterate. That is only 1. So this maximization may have the parameter x0, but we are not going to do that. We are going to do this, and you will see why this works. Okay. Then our objective function can be written this way. Am I right? Okay. Now, check whether is this true or not. obviously is true, right? We already know this is a positive value. Okay? So maximization and minimization can be interchanged like this, right? Now, is it then true? Yeah, this is true. See that? This function may achieve some value at a specific x. Right? And at that value, this part, this vector, may be lower bounded by this one. Okay? And second factor can be lower bounded by this one. They are all non-negative values. Right? So what? So now let's apply our Rayleigh's theorem or Rayleigh's inequality. What is the minimum value of this one? Minimum eigenvalue of Q. Let's say that is lambda mean of Q. Then what about this one? We may say that lambda mean of Q inverse. Right? But what are the eigenvalues Q inverse? Inverse of the eigenvalues Q. So actually, what is this? 1 over lambda max of Q. Okay. So you may say that lambda mean of Q, lambda max of Q. Okay. And you can do something similar for mean of gamma k, right? So let's do it. So here, let's replace this max with mean, and then we have mean here and max here, and what? We want to flip the inequality and replace these two, max and max. Right? And what happens? This becomes lambda max of Q times lambda max of Q inverse. And this becomes what? Lambda max of Q divided by lambda mean of Q. Got it? Got it? Okay. Now what can we say? So, minimum of gamma sub k is greater than this one. Okay, is it correct? Seems wrong. Okay, just a second. Let me see. Oh, okay. Something's wrong. Okay. Here, I put something wrong. So, be careful. Here, this inverse, right? Got it? Because we track the value. Okay. So this one inverse, right? Okay. So entire thing inverse, this one inverse, this one inverse. Here the same. Okay. So we can say that max of gamma sub k is what? Let me see. I should be careful here then, right? Yeah. Confusing. Okay. Max inverse, mean of inverse, right? And this is in the numerator, and so I have to have this one, right? So something like this. Okay, so max is greater than or equal to what? Am I correct? Oh, sorry, something is wrong. Okay, so this way. Confusing. So lambda max of Q divided by lambda mean of Q, and similarly mean of gamma K is greater than or equal to lambda mean of Q lambda max of Q. Am I right? Okay. So gamma sub K is definitely greater than 0. So we can apply our result, right? And we know the descent property holds for descent, the steepest descent. And now the minimum is greater than this one. What does that mean? When we sum up gamma sub K's, it blows up because this is a positive number. Okay. So what does that mean? Our steepest descent algorithm, even though it has the zigzag property, anyway it converges to the global minimizer. Got it? Okay. So we are done. So this is important. Actually, this is not necessary for our proof. Okay. We prove that gamma sub K is less than 1, showing the okay, that holds because our V of x and V of x sub k and V of x sub k plus 1 are all positive. Okay, so that is less than or equal to 1, even though it says this is not a tight upper bound, right? And this is what we want. Okay, so yeah, as you see, gamma sub K is greater than or equal to some number that is less than 1, but it is positive. So if you sum gamma sub K's, then that sum is greater than or equal to this sum, infinitely appearing. That is infinity, so this sum is infinity. Got it? So we have proved our global convergence. Now we consider the another gradient algorithms. So remember this. So this is all the set of all iterative algorithms, and the variable step size, gradient, descent, and here we've just checked steepest descent resides here, and now we are going to check actually this one. Okay. But we start from general fixed step size gradient algorithm. So a general, not general, a fixed step size. A fixed step size gradient algorithm is going to be considered and applied, of course, to find the global minimizer of V of x, the quadratic function. Okay. Now, how does it described? It is an iterative algorithm, so the k plus 1 iterate equals the k's iterate plus what? Step size times the such direction. Now our step size is going to be fixed, okay, as the name says, as an alpha, okay, and alpha is chosen to be positive. So we can say this, where of course g sub k is what? The gradient. And especially in our V of x, what it is? it is q times x minus something b. Okay. So anyway, so this is our form. And since we have so if this substituted v of x, what happens to that 1 minus gamma sub k? Okay. So if we replace this one here and find gamma sub k, what happens? It's a simple substitution that shows that gamma sub k, actually we've seen already in the gradient method, alpha times g sub k transpose q g sub k divided by g sub k transpose q inverse g sub k times 2 times gk transpose gk gk transpose q gk minus alpha. So this gamma sub k is nothing but what? The gamma sub k for the actually general gradient method applied to v of x, where alpha is replaced by alpha k is replaced by alpha. Okay? Nothing different. Now this algorithm combined with some alpha may reside in here or here. We don't know yet. Okay? It depends on the value of alpha. For example, if we choose some very small alpha, like minus 1 million, what will happen? Minus 1 million is 2. And you have, let me see. Yeah, gamma sub k is some negative value, right? Minus 1 million, this is positive. And this is positive, and this is plus 1 million. Okay? So this is something like minus 1 million. Now replace it here. What will happen? It has ascend property, right? So depending on your choice of alpha, when this is applied to the v of x, it may reside here. Okay? If we choose some alpha, hopefully it resides here. Okay? And here goes our claim. Okay? This is very interesting and important, especially if you study adaptive signal processing. Okay? And you may say that why is it is related? In adaptive signal processing, in many cases, you want to find the global minimizer over quadratic function. And you may say that it's too simple. I don't even need to use an iterative algorithm. You are right if our objective function is clearly given. But in signal processing, what happens is this. You need to estimate your objective function from your observation. And your estimate has some error. So what happens is that you kind of repeatedly update your estimation of the objective function. And also at each iteration, you try to find the global minimizer. Okay? So this algorithm is very important when this result is very important when you try to find out a fixed step size adaptive algorithm that tries to find the global minimizer of an unknown quadratic function. Okay? And this theorem says something very interesting. This is the result. If you choose the step size as a positive number and some number less than 2 divided by the maximum eigenvalue of the symmetric positive definite Q matrix, then your fixed step size gradient algorithm converges to the global minimizer. Surprising, right? And of course, here Q appears. What does that mean? This theorem is true only for what? Quadratic positive definite Q function involved in your objective function. But anyway, very interesting. Okay. See that? You don't need to find or estimate every eigenvalue. You only need to estimate the maximum eigenvalue. Okay. And actually, there is a method called power iteration, okay, or power method. Or power method to find the maximum eigenvalue and the eigenvector associated with it, given a positive definite matrix, actually. And also there are many variations, like adaptive version, okay, recursively estimating the largest eigenvalue. So when I was a graduate student, my senior in the lab developed some algorithm. And then also wanted to find a global minimizer of some quadratic function. And he put the constraint for the step size, and at the first glance, I could not understand. Even though I learned this theorem in the optimization theory course. And actually, this was the result applied to restrict the step size so that his adaptive algorithm theoretically converges to the global minimizer. Anyway, so we are going to prove this theorem. How? So here, this theorem is very strong in the sense that it's an if and only if theorem. Okay. So it has what? This direction to be proved and that direction to be proved. But usually we read this one as if and only if. What does that mean? If this is true, so if part means that if this is true, then this is true. So actually, the if part is this direction. Okay? And you say that direction is a direct part. You say this direction as the converse. Okay? So we are going to prove two results. And let's take a look at our note. So first, we are going to prove if part. Okay? So if the fixed step size is chosen that way, sorry. What is if? Let me be careful. Okay, so it's kind of reversed. Okay? This holds if and only if this is true in our textbook. So if part means that if this is true, if the step size is chosen this way, we have global convergence. Okay, so let's prove that part. Okay? And actually this part is also related to the Rayleigh's theorem. Okay? So we can show that this gamma sub k, if we choose alpha like this, can be shown to be greater than 0. Okay? And again, this is always bounded by 1, right? Because we have quadratic objective functions. So this value is between 1 and some positive value greater than 0. What does that mean? It goes to global minimizer, because some of gamma sub k's will blow up. Okay? Now, how can we show this? It's not that difficult. It's a little bit confusing, but it's not that difficult. Okay, so you do it. Got it? And now, the converse. Okay. The textbook have a different approach from this lecture note. And actually, this lecture note is easier to understand. So lecture note proves using the proof by counterposition. So they assume that alpha fixed step size is chosen the other way. Okay? It is chosen as a non-positive number, or it is chosen as a greater value than 2 over lambda max. Okay? And you don't need to prove that it always does not achieve global convergence. You just need to show one instance. So they cleverly chosen which direction? The largest eigenvalue direction. Because anyway, the step size is related to the eigenvector that is associated with largest eigenvalue. Actually, this can be easily understood if you reduce the problem into a one-dimensional case. Okay? So consider you have y equals x squared minus x, 2x plus 1. Okay, that is x minus 1 squared. Suppose your step size is too large from here. What will happen? You may just move around without converge to 1. Okay? And this step size is definitely related to this second order coefficient. Okay? For example, you fix step size, for example, to 2. Okay? And this constant is very large. What does that mean? It looks like this. Okay? Then may not converge. Okay? Got it? Okay. So that is the idea. So among many directions, you choose the direction parallel to the actually exact let me see. So what you choose is that you choose this direction, okay, parallel to your Q of Vmax. Okay. Of course, Q of Vmax is proportional to Vmax. Vmax is the eigenvector corresponding to the largest eigenvalue. Okay. So initially you start from here, okay, by setting this to 0. And then what happens is that when you update this k, you always have x sub k minus x star proportional to Vmax. Okay. So you always, your such direction is always proportional to the eigenvector corresponding to the largest eigenvalue. So you choose that one intentionally. And if you can show that this choice does not give you global convergence, you are done. Okay? And it shows that gamma sub k is always less than or equal to 0. What does that mean? You have...
It is time to wrap up. Dr. Cho, it is time to wrap up. Doctor.
This is not what I intended. I intended to finish this chapter today. Okay. Anyway. Okay, so you remember this formula again and again. So this is less than or equal to 0. What does that mean? This 1 minus gamma sub k is greater than or equal to 1. That means this updated value is greater than or equal to previous one. And we started from what? The Vx0, that is positive. Okay? So it never goes to 0, this value. Got it? Okay. So in that way, that theorem is proved. Okay. Now, should have to avoid this one. What can I do? Okay. Probably I have to do it on Wednesday. Anyway, the next chapter, chapter 9, is not that long, so I hope I can finish it as scheduled. Okay, that's all for today.